Okay, let's talk about limits of piecewise functions. So the thing to look out for is um, this number right here, as they're asking, what does the function look like as you approach an x of -2 from the left-hand side, okay? And notice how in this piecewise function you have one piece um, that you're only supposed to draw for the x's that are less than -2 to the left of -2, right? So I don't know what this looks like. It's probably some sort of curvy thing. You don't really care, but it's headed towards something as x approaches -2, right? And this piece only, this piece is kind of drawn up till x being -2. So when they're asking what the limit is as you approach -2, all you have to do is find out what this is when x is -2. Well, I know it says x is supposed to be less than, not equal to, but it doesn't matter because where x is -2, this is where it's headed. Yes, when you get there, it's at x equals -2. It might be something else altogether. But remember, limits are about kind of the destination. And the destination is -2 for the part of the function that is on the left. So where is this? Again, when you get there, you're going to you draw an open circle for x equals -2 for this part, but it doesn't matter for the limit. So let's figure out what this is when x is -2. I'll just plug it in. 2 squared. That's my x. This is x. So 2 minus, and I'm going to square that. That's a positive 4. This is where it's headed. This is where it's going, to a y of -2. And so the limit as you approach -2 from the left is a y of -2, or the y value is -2. Again, with limits, you don't care what is happening when you get there. In fact, when you get there, the piecewise function says at x equals -2, convert to the x minus 2, convert to this piece of the function, and it just jumps down here. But where you're headed and what this function, part of the function, is about, the shape of that function is this. So plugging in -2 will tell you where you're headed, even if you don't actually get there. As weird as that sounds. Okay, so for this piecewise function, you're asked to determine the limit as x goes to 4 from both sides. Positive, there's no positive or negative symbol. So this is a function where at x equals 4, to the left of it, it looks like this. And to the right of it, it looks like this. Okay? We don't really care. You don't really need to know what it literally looks like. But, I mean, it could look like something weird that goes here. And then this is for x less than or equal to 4. And then for the other one, maybe it's something like that. Or maybe it's just one continuous thing as they approach the same. We don't know. We don't know if it's this. We don't know if it's kind of like a split. But if it's this, there is a limit. If they're both headed toward the same value, and you know what? It could be an open circle when we get there. It doesn't really matter. Open circle or closed. If they're headed toward the same value, the limit exists. If they're headed towards split values, a y that's bigger here and lower than that here, then the limit does not exist. Well, all you have to do to find out is just plug in the x of 4 here and here, see if they're the same number. Okay, I just did it here. I plugged in 4 for x here. That's my x, 4. So for this piece, comes out to 5. And here's my x for that, 10 minus x squared. And plug that in, and I'm getting, so 2 different values, okay? One is headed toward 5, and I guess that's the top one. From the right-hand side is headed toward 5, or that should be an open circle, and from the left-hand side is headed towards -6. D&E, they're different. Oops. Okay, so let's review. To find that limit x approaching 4, period, we must find the limits from the left and the right. Find the limit, we use the rule to see which part of the function we're using. That's the left part of the function, so that was the -6. And then the right-hand function, or right-hand limit, we use the top piece. They're different, so it's D&E. Simple rule. Now let's talk about rational functions. For rational functions, I'll just cut to the chase. You are looking for the presence of a whole, or a VA, or neither. See if neither of them exist. Okay? Here's the thing. You've seen this with rational functions. If you're looking for the limit as x approaches the y of the whole, I meant to say the x of the whole, the value is, the limit is the y of the whole. If at the x that you're approaching, you have a vertical asymptote, that means on either side of this vertical asymptote at this x, maybe you have something that climbs up, maybe you have something that climbs down. There is no limit. There is no limit. Limits that where the y approaches infinity or negative infinity don't exist. So if we're going to analyze this function, we've got to factor it, because the only way you see any of those things are in factored form. So here we go. Yeah, what I'm seeing here is that top and bottom have GCFs. X is my GCF for the top and the bottom. Here it is in factored form. Now, the rule, whole, you have the same factor on the top duplicated in the bottom. So what factor is that? It's this one. Okay, so you do have a whole at, and what's the 0 of x? It's 0. 0 is what makes x 0. So you have a whole where x is 0. If we were to do this like we did in the rational functions unit, we take that 0, we would cross, to find the y of the whole, we know the x is 0. To find the y of the whole, we would plug in that 0 here, and what we get would be the y. Let's just go ahead and do that whole thing, because you're going to need it to answer this question. So we're getting -7 over -1. In other words, the y is 7. Okay, so the whole location is 0, 7. Well, what's the question? So as the limit, what is the limit as x approaches 0 of this function? Well, we just kind of have defined it. We're saying that as this rational function approaches an x of 0, there's going to be a hole. And we have actually figured out that the y of the hole is 7 because we found the coordinates of the hole. And remember, a limit when from the left and the right-hand side are approaching the same value, the limit is that value. Doesn't matter what it looks like when it gets there, because when it gets there, the function isn't defined. Limits don't care. Factor, cancel common factor. There is a hole at the value of x equals 0. So you must find the y coordinate of the hole, which we did. Here's another. Remember, you're looking for the presence of a hole or a VA, or maybe it's neither. Okay, first thing to do is factor this. There's my GCF. Okay. Okay, so here we have a hole. It looks like we have a hole at x equals 5. We don't know the y. We have yet to do that. But we also have this factor. Remember, x alone is a factor. Sorry, it's not a binomial, but it is a factor that's alone in the denominator. So we have a VA at the 0 of an x is 0. We have both. Okay, so fact is we have both. Well, where is the limit asking us to look? They're asking us to look at where x approaches 0. So this doesn't matter. Who cares what's happening at x equals 5? Yes, there's a hole, but the limit is asking, what is the y value turning into as x approaches 0 from both sides? And you know what? What you have there? You've got this. So the function, you know what happens around vertical asymptotes is either doing this or this or, sorry, this or that to the left and to the right of that vertical asymptote. And what does that spell? That says D and E. Okay. So again, whole vertical asymptote, but this will tell you where you should be looking and whether you're going to be looking for the hole or the vertical asymptote. Okay, this one we've got a factor as well. Let's factor it up. Okay, needed x method for this. This had a simple GCF. 1, 2, 3, 4 factors. Okay, nothing. We've got no repeaters, so there's no holes. But this is unique. This is by itself, obviously. There's no x upstairs. This is by itself down. So you have two vertical asymptotes. Two vertical asymptotes. One vertical asymptote is here. The other vertical asymptote is here. Okay, so at x equals 0 there, at x equals 6, we've got another vertical asymptote there. The function is somewhere in between these guys. So now let's go back to the question. The limit as x approaches -6. Okay, -6 is out here, nowhere near these vertical asymptotes. So we don't know what the function looks like, but it's probably something like this. I don't know. Sometimes when you have two vertical asymptotes, sometimes it looks like that. But it doesn't matter. you're asked to look out here at somewhere around here. I don't know what the y is going to be. So what you're going to do, okay, this is a case where you're not at a vertical asymptote. You're not looking around the hole. You're just looking somewhere where the function is just a curve somewhere, and you need to find out the y value when the x is, say, somewhere there. And that's done by plugging it in. Let me take a quick detour and show you what that function actually looks like. Okay, so it looks like this. Okay, I was wrong. It didn't look like the way I was just totally guessing. But there's a vertical asymptote here, and here's the vertical asymptote at x equals 6. By the way, this is the non-factored version, the standard form. This is when it's factored, and of course exactly the same, but this is how we factored it. Okay? And all they want to know is, what is the y value when x is, what was it, negative 6? I mean, Desmos will tell you it's going to be that. Okay, but you won't have Desmos when you do the test, so you have to calculate it by hand, which is simply just plugging it in. And I just did it right here to save time, and it's exactly what we saw in Desmos. It's negative 1/4, or negative 0.25. These next three are fairly simple, limits to infinity, three different types. And this is a callback to rational functions and your favorite, the horizontal asymptote. And remember, there are three cases. There's top heavy, bottom heavy, and there's even. And there are three different things that you do when you encounter these three scenarios. And they're all determined by the highest degree term. The term that has the highest exponent, you could ignore everything else, both on the top and the bottom. So first, let's identify that to see which of these scenarios we got. I'm seeing this as the biggest exponent, and I'm seeing this as the biggest. I should capture that. 28 to this to x to the 6th power. Okay, so this is bottom heavy. Bottom heavy. What this means? It means y equals 0. It means that this number, when x gets really large, is so large, this is just pusillanimous. That means very, very, very small compared to this as this gets large. It's so large that it's like 1 over something. 10 gazillion is practically nothing. So as x approaches infinity, y is going to approach 0. And what it looks like, here's our horizontal asymptote, and here's our function going all the way to infinity, or it could be coming from the top. I don't know. Doesn't matter. But as it goes off to infinity, this gets lower and lower and lower and lower, but it never touches 0. It gets very, very, very small, though, or from this end as well. Okay. As we see here, the denominator grows much faster than the numerator. The bottom grows much faster than the top, making the limit equal to 0. Scenario 2. First, we have to find the largest degree term. And this one's the largest down here. Same degree, 4 and 4. So we have an even scenario. And when it's even, you make a fraction out of the coefficients, okay? Meaning the 8 and the 7, okay? So as the function veers off to infinity, the horizontal asymptote is just where it levels out, and it's going to level out at 8/7. Limit is equal to the ratio of the coefficients. And then your third type of example, let's check out. This seems to be the largest. And this one is the largest on the bottom. So you have top heavy. And if you remember, if it's the higher degree by 1, you get a slant asymptote. Or if it's by more than 1, you don't get an asymptote at all. You get a function that just goes wildly off into infinity. And maybe on the other, negative infinity. Doesn't even approach like a diagonal line. It just, either way, there is no limit. Top heavy, no limit. Doesn't exist. So those are 3 rules to take note of and memorize. Okay, last type of function for which we have to find limits. This is going to be unfamiliar to you, so this is something new. Like, look at this function. You've never seen anything like this before, but there's a couple simple rules that you can apply to figure this out. Okay, these are called radical expressions. Here's our radical. Just so you get a sense of what this even looks like, let's just take a quick peek. Put that into Desmos. It's right here. Okay, it looks strange. Okay, but they're going to pick an x somewhere out around here, and they're going to ask you what the limit is as you approach that x. And you're going to have to figure that the left hand and the right hand, both of them, you're going to have to figure out, because they don't tell you to just look from one side or the other. It doesn't have a little plus or minus symbol there. You have to look from both sides. Okay. But it's more of a mathematical exercise, since it's hard to visualize what this is going to look like, and you won't have Desmos on a quiz or test. So here's the first thing you're going to do is see what happens when you do plug this in. See if you even get a number that you can work with, because if you do, then that's the limit. I mean, you saw here, it's very continuous. Doesn't break up like a rational function. If your function ends up as just a number, that's really what it's going to be approaching, whether you're coming from the left or the right. So let's plug in a 12 right there. Plug in that 12, plug it in right there. Well, the top is definitely going to be 0. And 12 minus 8 here is 4 under the radical. Oops. Yeah. Square root of 4 is 2. 2 minus 2 is 0. So this is not something you can analyze. You can't, even if there was a hole at x equals 12, if x is 12 and somehow you have a hole there, that doesn't mean there's no limit. There can definitely be a limit, because if it's going toward that hole from both ends, there definitely is a limit. This doesn't really help you much. You've got to use, this is something that tells you what you need to do with some fancy math tricks to get at the value that it's headed toward, okay? And here is what you do. You're going to exploit this rule. Remember, if you have a minus b, okay, and you multiply it by a plus b, you end up with a squared minus b squared, okay? This is dots, difference of two squares, okay? This is difference of two squares, but this is what it is. This is how you create that difference of two squares, by just taking the a and the b and making a new binomial by just flipping that sign. You keep the a and the b, okay? So what I'm going to do is, this is called a conjugate. This is the conjugate of this, and they're conjugates of each other, okay? I'm going to get rid of this nasty radical sign by multiplying this by its conjugate, okay? Here's my a, x minus 8. I'm going to switch that sign to a plus, and there's my b, okay? Put parentheses around that, okay? But whatever I do to one side, oh, well, no, scratch that. If I'm multiplying an expression by 1, then I'm not changing the value of that expression, which is what you want. So I'm going to be multiplying the top by the same thing. Okay, same kind of over same. Now, I know this looks really nasty on top, but the bottom is going to simplify very nicely, because following this pattern, when I multiply this binomial by that binomial, all I have to do is square the a value, and when you square two square roots, it just cancels out the square root. That's what I get. But of course, if it's difference of two squares, I have to respect that difference and make sure in my answer I have a negative, and then I square the b. 2 squared is 4, okay? And the top, I'm going to leave as this kind of crazy, nasty looking thing for now, okay? But look at the bottom of this expression, okay? X minus 8 minus 4. Let me do a rewrite. X minus 12. And I'm going to rewrite the top. Interesting, right? All I have to do is put parentheses around that, and you can see the duplication. I have a factor up here, x minus 12. I have a factor down here of x minus 12. Okay. And so when we cancel out, we replace with ones. And this is what I have in the end. I don't need that 1 in the denominator anymore, but all I have left is this, plus 2. And you can say over 1, it doesn't really matter. This is what I have rewritten this function to. So really, this is a better way to analyze the limit. The limit as x approaches 12 of this. Okay, and what I'm now free to do is plug 12 into my x, make this x 12, and see what I get. And that will be my limit. That is what the function will evaluate to. Well, the limit will be what this evaluates to. It won't exist there, because when you plug it into the original, you do have something undefined. So what is this? It's the square root of 12 minus 8 plus 2. Square root of 4 plus 2. Square root of 4 is 2. So it looks like we're getting 4. Okay, let's check that out on Desmos. See if when we hit the 12 for our x, whether we get a y of 4. Let's see. When x is 12, y is undefined. Well, we knew that, but to the left of it, or to the right left of it, we're getting 3.9, 3.96, 3 point, very, very close to 4. We're approaching 4 from the left. It's getting even closer to 4. And then from the right-hand side, we're at, 4.1, 4.06, 4.04, 4. When we get there, it's undefined, but that doesn't really matter. So again, we're approaching a y of 4, 4.05, 4.04, 4.01. Oh, yep. So you can see that. If there was a table that got us closer and closer to a y or an x of 12, the function would be getting closer and closer to 4. But when we get there, it just goes into being undefined. This is from the right-hand side. Okay. Use the conjugate. This is the cancellation, the magic cancellation of the x minus 12 over x minus 12. Okay. Last problem. That was the hardest one of this set. But same thing. First order of business, see if this evaluates the thing, just to a definite value. And if it does, your work is, you don't have to do that crazy conjugate rationalization thing. It's just kind of what that number is. So x approaching 3, so let's plug in the 3 for our x. 3 plus 6 minus 8. Okay, so it looks like the top is 9 minus 39, and the bottom is, this is 9, and square root of 9 is 3, so 3 minus 8. 9 minus 39 is negative 30. Okay, 3 minus 8 is negative 5. That's just 6. We lucked out. We lucked out. The limit as x goes to 3 is 6, because when you arrive at 3, you're at 6. So a little bit to the left, a little bit to the right, you're going to be around 6. Okay, let's check this one out graphically as well. Okay, here's that function. As x approaches 3, getting there. Oh, it lands at 6. So the approach is going to be, from the left, you're definitely approaching 6, getting closer and closer and closer to 6. And from the right, you're definitely getting closer to 6. 5.83, 5.65. I'm sorry, I was reading that with the y's. 3.75, 3.4, 3.2, 3.1, and that's where you arrive. But this is what matters, is that you're getting closer and closer to 6. Same over here, 2.5, 2.999. Anyways, okay. Six is your answer. Substituting 3 for x does not result in indeterminate form. Indeterminate form is 0 over 0. That's the way Delta Math defines it. So the method of substitution may be used. Just plug in the 3.